Hello. That's better. Today I'll be talking about high-performance logging. This is not just about logging, but also some of the design decisions behind the libraries that implement this logging. But so who are we? I have a small company of developers. We focus on low latency infrastructure within Java. And we also do bespoke development and training, consulting. Some of you may have come across my name before because I've got slightly over 10,000 answers on Stack Overflow, Java. So what are the problem space that we're interested in? We mainly interested in how you deal with data, how you persist data. And the reason why persistence is important to us is that this leads us to being able to develop deterministic systems. You want to have systems that behave the same way every time and in a replayable manner. For example, in the trading environment, if you're dealing with, say, FX, which is exchange rates, or fixed income, such as interest rates, the minimum trade size is typically $1 million or pounds. So you only need one trade lost or one trade going the wrong way to lose quite a bit of money. So we want to have a system that will behave the same way every time, not just in terms of what it does, but also its timing, because timing is a feature of a trading system. You need to trade within a certain time frame, or otherwise you're likely to lose money. And certainly if you work for a hedge fund, to trade slowly, you're better off not trading at all than trading slowly because you will lose money. And if you don't trade at all, of course, it doesn't cost you anything. So we've developed a group of libraries that are designed not only to scale horizontally, which is the main focus of a lot of data grid systems, but also to scale vertically. That is that you get much more performance out of each box that you have. As a result, many of our clients only have 1 or 2 boxes because that provides all the performance they need. The largest cluster we have is 6. And they take an opera feed through that cluster, which handles 25 million events a second. And since very few clients are trying to handle and persist 25 million a second, they've never gone beyond 6. But in terms of logging, this leads to an interesting question. If you could record every message that came in and out of your system, everything that you might want to know about your system, and you could do it in such a fast way that it had almost no impact on your application, would you ever need logging levels? Would you just not record everything? Because the most common reason why people turn off logging levels, there's 2 reasons. One of them is that it impacts your performance. The other reason, which is quite common, is that you're worried about how much disk space you're using up. Now, the thing about disk space is it's getting cheaper and cheaper all the time. If you work for a large bank, then they find interesting ways of making disk space very expensive. But if you don't work for a large bank, buying a few terabytes of disk space doesn't necessarily cost you a lot. So, so how does Chronicle work differently? We use things called memory map files. So this applies for all of our libraries, but it also applies for our logging. So for logging, we persist data to a memory map file. The reason we do this is that it's a synchronous copy. So we copy the data to a memory map file by just writing to raw off-heap memory. And then once that is finished, that's done. The application doesn't need to do any more. It's synchronous, so you don't lose messages if your application dies. The only time you're at risk is if the machine itself dies. Because if the machine itself dies, it won't necessarily have gone to disk. So we also support replication. So if you have a machine failure and the data's been replicated, then hopefully the second machine won't die as well. You can also replicate to more than 2 machines. We've got a low-level library called Java Lang, which is what all of our libraries are based on, including the logging. All of our products are designed to handle millions of reads and writes per second. We target microsecond latencies, which means that you can do millions of reads and writes per second in a single thread. And a lot of cases when they talk about dealing with, say, 1 million operations per second or 1 million transactions per second, they're actually talking about thousands and thousands of threads. For example, one popular database, they can do 1 million transactions a second on a 24-node cluster. The average latency is 46 milliseconds. Now, to get 1 million transactions per second with a 24 millisecond latency, you need 46,000 threads. Then the question is, well, what if I don't have 46,000 tasks that I want to do at once? Well, if you've only got 1,000 tasks, then you've lost 98% of the throughput. So the nice thing about this approach is that even one thread, even if you've got a task that's single-threaded that can't really do lots of things at once, you can still achieve this kind of throughput. And in fact, a lot of complex business logic is not inherently parallelizable. It's not easily parallelizable. As mentioned, it's synchronous. The reason that's important is that when an application dies, often the most important message is the one just before it died. So if you're using an asynchronous logger, quite often you can lose the last message that told you why your application died, which is kind of defeats the purpose. Now, as I mentioned, if you pull the power out, you might lose the last message, but then again, there's probably no point debugging your application as to why you pull your power out. So it's probably not an application fault in that case. It's Apache 2, so which means that it's all free. You can read the source on GitHub, and so there's no reason not to use it from that perspective. So getting on to logging specifically. What Chronicle Logging does is that it provides adapters for our Chronicle queue, which is our journaling library. Now, writing to Chronicle queue is great if you have a greenfield application, but what if you don't have a greenfield application? So what we do there is that we provide adapters so that you can, just by changing the configuration of your preferred logging framework, you can have it write to a Chronicle queue instead. We get similar performance to Log4j2 when it's using asynchronous logging. And the other thing is that it can be read in real time. So a lot of logging frameworks, some people have written scrapers to kind of read a log to process it downstream. This is actually designed to be read in real time by another application. And that's because the queue is not just a journal, it's also an inter-process communication mechanism. So it is designed to be read by a program. The reason is, if you're logging millions of events per second, it cannot be read by a human. It has to be read by a program anyway. So it's not practical to just write it all out as text and expect some sysadmin to grep through it a couple hours later. We support TCP replication for queue. So what does queue do if logging is based on it? It's designed around reactive programming, which, as I said, if you've got a greenfield application, it's very easy to put reactive programming into your application. If you've got a brownfield application that exists already and is not designed for reactive programming, that's a bit more work. But if you've got an existing application, just replacing the logging is often the first thing that developers will do, because that you can change, right, quite easily without changing your application too much. We can sustain throughputs of 40 million messages a second with queue. That's to a single queue. Actually, if you have multiple queues on the same box, you don't actually get any more throughput, because one queue is enough to exhaust all the resources of your box, use up all the resources. So In fact, what some people do is they have one queue for their entire application. Everything goes through that one queue. And then you've got a complete history of exactly everything your application did, in what order, and this adds to replayability. Whereas if you've got lots of logs across your system, it can be difficult to reconstruct exactly what was the order of actual events. So say you've got millisecond timestamps, and you've got 5 events that all occurred in the same millisecond, and they're written to different logs. Which order did they go? The reason that matters is sometimes when you're looking at sort of very multi-threaded issues or bugs, the actual order these events occurred can matter. As I mentioned, queue is really, it was originally designed not so much for logging, but for inter-process communication. So for communication between processes on the same box, say you've got a CEDAR model where you've got staged event-driven architecture, then you want to be able to pass data between threads very efficiently. So we get latencies for a typical message size. And by typical, we usually have small messages because smaller is faster. We get about 200 nanoseconds. You can actually get lower than that, but that's only for really small messages. The actual bottleneck, as far as we've tested, seems to be how fast the OS can reclaim pages. And in fact, we can sustain rates of about 400 megabytes a second, and we can get peaks of over a gigabyte a second. And because it's pure Java, the same libraries run on, we tested it on Windows, Linux, and Mac OS, the supported operating systems. Now, queue is good, but sometimes you don't want to record every event. So this is where having a low latency key store is perhaps more useful. The difference between a queue and a key store is that a key store will keep the latest value for a given key. So you construct a unique key for each entry. In trading, it might be something like an instrument. You want the latest price. You don't always need to know the entire history. You just want to know what the current price is. So you store this in a key value store. It has very similar properties to logging, and the only difference being that because you're not necessarily expecting to record every message, and you may have a high fan out for this kind of data, we also support UDP replication. Whereas for queue, we only do TCP so that we can deliver every message reliably. So what does this look like for an existing application? So say you've got a main application and you've got certain data structures within your application. With these kind of techniques, and in this case I've got Logger sitting down the bottom there, just sort of as a service to all the rest of the application, then you can store all your data off heap using this. Now, one of the important things that I haven't mentioned about off heap is that it has no GC impact. So you can store as much data in these off heap collections and not increase your GC pause time. So a lot of people put it in just as a performance boost. But in this case, when it comes to logging, the issue is around monitoring your application. And the benefit of having these shared memory structures that are off heap is that you can tap into these shared memory structures from other JVMs. So in this case, you've got, say, a main application that you've got is existing, but you want to see what your application is doing without slowing it down, without impacting it. Well, what you can do is you can run up another application. It's tapped into the same shared memory map files. It can see what your main program is doing, and it can do this with almost no impact to your main application. You can even do things like little command line utilities, because it's very quick to bring this up. You can map in gigabytes of data very quickly, typically around well under 10 milliseconds. So from a command line point of view, 10 milliseconds is nothing. And the nice thing about the command line is that not only can it view what your application is doing, it can alter it. So it can alter your maps, for example, because it's thread safe across processes. So you can change controls within your application, but do it in such a way that your main application doesn't need to know too much about what you're doing. It just allows you to change some live data structure. And because it's so fast, you can do this quite happily in production. You might be used to doing this maybe in development when you've got a debugger, try something out, I want to change something. But you would never consider doing that in production, whereas this is fast enough that you can. Here's another example based around microservices. So unlike the previous example, you have one application, and what you've basically done is you've just made it easier to manage and see what it's doing. Whereas in this example, you're starting to use these data structures and these queues and the logging to share work between multiple applications. So in this case, a client gateway has requests coming in. It can distribute those requests and get that work given out to a number of micro applications. Now these micro applications, because we support replication, these micro applications can actually be on different machines. But in many cases, with machines getting bigger and bigger, they can run them all on the same machine. We've got one client who uses this kind of structure, mostly the map rather than the queue. And they have a 240-core machine, 3 terabytes of memory. They have 30 JVMs running on this box. So they want to share their data structures with 1 copy of memory, rather than having 30 copies of that data being replicated between the JVMs and using up heap. Whereas their 50 gigabytes of shared state, there's 1 copy, it's off heap, so it has no GC impact on any of the programs. And to alter it for all the programs, they just change the memory once, and that's visible to every JVM simultaneously. So this slide actually explains why so much of this is not about logging. And that's because we've gone to some length to make it really simple to just drop it in. And you just change the configuration file to use a different appender, and that's it. So then I'm thinking, well, what else can I say to make the topic more interesting? So essentially, for each, so these are the ones we support: SLF4J, Log4j, and Logback. We don't have the Sun logger yet, or the JDK logger yet, but we've got that on the roadmap. So coming on to performance. Why would I use logger rather than the underlying library? And here's a good example. If you use logger, of course, you've got code that you've written already, and this is the example I benchmarked. It's as a single log line, it's a lot simpler to use logging. Now, the underlying library is a lot more efficient, but you have to write quite a bit more code. You have to write out all the information that's associated with the message, and clearly it's a bit more painful and doesn't work if you haven't written your code this way. But the second one shows you in a bit more detail as to exactly what is being written. It's putting out the timestamp, the thread name, a format message, and 3 values. So how does it perform? Well, in all cases, it is faster than not using Chronicle Q. In some cases, it's a lot faster. I'm not entirely sure why logback is, for our test, was so much lower. But in each case, you saw improved performance. What you don't see here is that you also see less garbage being created in terms of its persistence. Another thing you don't see is that with Chronicle Logger, it's synchronous logging. The other examples are asynchronous logging. So like I said, you risk losing a message. For Log4j2, which is one of the faster examples, we still take about half the time. Log4j2, for example, has got the disruptor in it for taking lots of messages at once. Now, why use Chronicle Q alone is that it supports concurrent writers. So with concurrent writers, it scales a lot better. So if you, in all these examples, they run with 32 threads. But if you run it with Q, which is concurrent, it kills all the others in terms of performance. Even single-threaded, it's faster. But yeah, once you've got to 32 threads, hopefully you don't have 32 threads that all they do is log. So it's a slightly unrealistic example in that case. But you can see that it has very little overhead. In any case, you're all dealing in this sort of microsecond level. Yes. Okay. So I can talk a lot more about the details of how this actually works and what's going on under the bonnet, but I thought I might leave that to questions. So please ask questions. How does it really work? Okay. How does it really work? The way it really works, and this gives you an example because these two are equivalent, is it translates this first logging line into the second logging line written out. What this logger does, it reserves an area of memory on the memory map file. This memory map file, to be concurrent, is there's one per thread. So there's a file for each of the threads, so they can write concurrently. Then it writes out this raw data, which is pretty much as binary as possible. There's also a text version, but the text version is slower. And as you can see, like for example, this write int turns down to just a couple of machine code instructions in reality because it uses intrinsics that are in unsafe. So intrinsic, the difference between that and native is that the JVM recognizes certain methods. And instead of making it a JNI call, it just replaces it with the machine code that's equivalent to. So some of these operations, particularly these last three, and this one are very efficient. We're talking maybe 5 to 10 nanoseconds. It's extremely fast. And then this is the finish. Now, the finish is where a lot of the work actually happens. In this case, it has to add this entry into a single queue, right? So that you have a consistent ordering for all of these entries, which are now being written to different files. So all it does is it doesn't use locks. All it does is it keeps trying to append to the queue, the index, to say, where is my next entry? And it can do this with just a single cas operation. Because it's append only, it can say, try and set this from 0, which is unset, to my new value to say where to find the entry. And that's what cas does, is it allows you to compare and swap. If that fails, it means that another thread tried to come in and write an entry. So it just keeps going through the queue, just keep getting longer and longer until eventually it successfully writes. The nice thing about that is that it takes about 25 to 50 nanoseconds, and there's no locking involved. So that this finish can be done still there's quite a bit of work to do compared to the others, but it's very fast. So, yeah.
How does Chronicle Q compares to the Elmar's disruptor?
Okay, in terms of just throughput of messages per second, it's similar but not as fast. A disruptor can get into the order of 100 million messages a second instead of 40. The biggest difference is that the disruptor is a circular buffer, so whereas Q is an unended buffer, an open buffer. The reason that's significant is that when you have a circular buffer, you have to tune its size. So you have to say, I want it to be small, so it fits in memory efficiently. But I don't want it to be too small that it ever fills up, so that any slow consumer slows down my producer. right? So you've got this constant tension between wanting to be as fast as possible, because when you're tuning down to that level, these things matter. But also, I don't want to have delays, unnecessary delays in my system. The other key thing is that disruptor doesn't persist, right? And inevitably, you're going to have to write something to disk. Maybe not every message needs to be written to disk, in which case disruptor makes a lot of sense. But there's a certain percentage of key messages you want to write to disk. And that's where Chronicle comes in. So quite a few people use Chronicle sitting behind disruptor for this reason. So for the messages they need to persist, they go to queue Chronicle. And in some cases, they've decided that, well, actually, Chronicle by itself performs well enough. I may as well just persist everything, and then I don't need disruptor. Yes.
In Chronicle, do you have support for correlation between logs?
Not really. The closest we have is you can put nanosecond timestamps in it very efficiently, very quickly. The simplest thing to do is if you've got logs on the same machine that need to be correlated, you write them to the same log, because there's no performance impact for doing that. So that's the other thing that we do differently, is that when we say concurrent writers, they can be across multiple processes. So you can have 10 JVMs writing to the same queue without a performance impact, and it's thread safe. So then correlating it is trivial. Where it's a problem is if you've got logs on multiple machines, then you do need to have correlation. We've got support for replication, so you can aggregate logs across multiple machines. Then it becomes tricky because things like nanotime is not so good. It's difficult. You can do it, and I have done it, but it's difficult to synchronize nanotime across multiple machines. Yeah, it's a tricky problem in that sense. What you can also do is put additional fields. So say instead you're trying to not determine the order so much, but you want to correlate logs for a single request. So a request comes into your system, you give it a unique ID, and then you want to see what happens to that ID as it travels around your system. And then you want to see all the events that are associated with them. We do have support for filtering and querying the log, which case, if you've got a field that you've added that's unique to your request, you can search for it. But again, getting the precise ordering might be tricky if it goes through your system very quickly.
Any questions? Any other questions? No.
Okay.
That's all. Thank you very much.